The James Webb Space Telescope, JWST, has only been operational for a relatively short time, but it has already caused a seismic shift in the world of astronomy and cosmology. With its incredible ability to peer into the farthest reaches of space and time, it has given scientists access to a treasure trove of new data, some of which has defied all expectations and forced a re-evaluation of our fundamental understanding of the universe. In particular, JWST's findings about the early galaxies and the accelerating rate of cosmic expansion have caused a ripple effect, challenging theories that have held up for decades. Could it be that our current cosmological models are wrong? Are we missing something crucial that could change everything we thought we knew about the universe's birth, evolution, and future? Well, one of the most provocative ideas is that these discoveries could actually point to something unimaginable, like the possibility that our universe is colliding or merging with others. Though this might sound like the premise of a mind-bending sci-fi movie, it's actually a legitimate theory that has been explored in the scientific community and could hold the key to a deeper understanding of the cosmos. Looking up at the night sky is an awe-inspiring experience, and it often prompts deep questions about the universe. Where did all of this come from? How did the immense variety of galaxies, stars, and planets come into existence? In ancient times, people often attributed the creation of the universe to divine or supernatural forces. Today, scientists have a different approach, one that involves observation, measurement, and theory. By studying distant galaxies and measuring their distances, astronomers have pieced together a detailed timeline of the universe's evolution. According to the most widely accepted model of cosmology, the universe began about 13.8 billion years ago with the Big Bang, a hot, dense singularity that expanded, cooled, and eventually gave rise to the universe we know today. The Big Bang theory provides a comprehensive explanation for the origin of the universe. It posits that not only was matter and spacetime created during this event, but the very laws of physics as we understand them also came into existence. Since then, the universe has been expanding, and this expansion continues to this day. However, the expansion of the universe didn't just begin after the Big Bang and continue at a steady pace, it has accelerated. This accelerated expansion has been attributed to the mysterious force known as dark energy, which is thought to be pushing the universe apart. Despite its profound effects on the expansion rate, dark energy itself remains largely unknown, and scientists are still trying to figure out exactly what it is. Dark energy is an essential part of the current cosmological model, but it is still a largely theoretical concept. Its existence is inferred from astronomical observations, but it has not been directly observed. What we do know is that dark energy is responsible for the accelerated expansion of the universe, and its effects have been growing stronger over time. According to current theories, dark energy is thought to make up about 68% of the total energy content of the universe. However, despite our growing understanding of the universe, there remain many unanswered questions that the James Webb Space Telescope is now helping us address. For example, one of the most exciting aspects of JWST's discoveries is its ability to look further into the past than any telescope before it. JWST has already identified galaxies that appear to be much more developed than they should be, given our current understanding of how galaxies form. Some of these galaxies are so well formed that they seem to be already comparable to galaxies like our own Milky Way, despite being located in the early universe, just a few 100 million years after the Big Bang. This revelation raises a fundamental question: how could such massive, complex galaxies have formed so quickly? After all, our models of galaxy formation suggest that it should have taken much longer for galaxies to reach this level of maturity. One of the most mind-boggling examples of this discovery is the galaxy known as JWST 140. This galaxy was formed just 290 million years after the Big Bang. According to current models, galaxies at that stage in the universe's history should be relatively small, faint, and dominated by young stars. But JWST 140 is different. It already contains hundreds of millions of solar masses worth of stars, and its light has traveled more than 13 billion years to reach us. What's even more surprising is that scientists believe this galaxy must have gone through several generations of massive stars that lived, died, and exploded as supernovae, enriching the galaxy with heavy elements like oxygen. The presence of these elements suggests that the early universe might have been far more complex than we previously thought. This discovery, along with others like it, forces astronomers to re-examine their models of early galaxy formation. How could such large, mature galaxies have formed so quickly? Were the conditions in the early universe different from what we expected? Or could there be something more profound at work that we've yet to fully understand? The discovery of these early, massive galaxies may suggest that the universe was capable of forming more complex structures much earlier than previously thought. But this doesn't just shake up our understanding of galaxy formation, it also calls into question the very nature of the universe itself. Another crucial discovery made by the James Webb Space Telescope is related to the expansion of the universe. For decades, astronomers have been trying to measure the rate at which the universe is expanding, a key quantity known as the Hubble constant. According to the most widely accepted models of cosmology, the expansion of the universe should be uniform, meaning that the rate of expansion should be roughly the same everywhere. However, recent measurements have shown a troubling discrepancy. The universe seems to be expanding faster in some areas than in others, especially in our local region of space. This discovery has led to a significant puzzle in cosmology, one that has yet to be resolved. To understand this puzzle, we need to look at how the Hubble constant is calculated. Traditionally, astronomers have calculated the Hubble constant by measuring the cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang. This radiation fills the entire universe and serves as a snapshot of the universe when it was just 380,000 years old. By analyzing the CMB, astronomers can infer the rate at which the universe has been expanding over time. This method has yielded a Hubble constant of around 67 km per second per megaparsec, km/s/mpc, which is considered to be the standard value. However, when astronomers try to measure the Hubble constant using a different method, such as by observing supernovae or Cepheid variable stars, they obtain a different result. In these cases, the calculated value of the Hubble constant is higher, around 73 km per second per mpc. This discrepancy is known as the Hubble tension, and it has puzzled astronomers for years. What could explain this difference? Why do these two different methods yield such divergent results? The James Webb Space Telescope has added another layer of complexity to this puzzle. One of the key discoveries made by Webb was that the Hubble constant appears to be even higher than previously thought when measured using its advanced instruments. Specifically, the telescope has provided new measurements of Cepheid variable stars in distant galaxies, allowing astronomers to refine their calculations of the Hubble constant. These new measurements are in agreement with the higher values obtained from other methods, further deepening the mystery of the Hubble tension. So, what's going on here? How can the universe be expanding at such different rates in different regions? And why do these different methods of measurement yield such conflicting results? One possibility is that our understanding of the fundamental forces at work in the universe is incomplete. Could there be something we're missing, some additional force or particle that we haven't yet discovered? Or could there be something fundamentally wrong with our understanding of gravity? These questions have led to some radical new ideas, one of which is the theory that our universe could be merging with other universes. This theory suggests that the discrepancies in the expansion rate could be the result of interactions between our universe and other, parallel universes. According to this idea, our universe might not be an isolated, self-contained system, but rather part of a much larger multiverse. In this scenario, the Hubble tension could be explained by the gravitational effects of nearby universes that are influencing our own. If our universe is merging with other universes, it could cause the expansion rate to vary in different regions of space. This idea is certainly unconventional, but it is not without its scientific merit. The theory of a multiverse, a collection of parallel universes, is one of the more speculative ideas in modern physics, but it has gained traction in recent years. Some physicists believe that the laws of physics as we understand them may not be universal, but rather specific to our particular universe. If this is the case, then it's possible that other universes could have different laws of physics, and their interactions with our universe could explain some of the anomalies we've observed, including the Hubble tension. One promising avenue for testing this theory is through the study of the cosmic microwave background, CMB, radiation. As mentioned earlier, the CMB is the afterglow of the Big Bang, and it provides a snapshot of the universe's early history. If our universe is merging with other universes, it's possible that we could detect subtle imprints in the CMB that would reveal the presence of other universes. These imprints could appear as unusual patterns or anomalies in the radiation, which would be detectable with advanced telescopes like the James Webb Space Telescope. Interestingly, recent studies have suggested that the CMB may indeed contain clues to the existence of other universes. For example, some scientists have proposed that certain unusual patterns in the CMB could be the result of collisions between our universe and other universes in the multiverse. If these collisions occurred in the early universe, they could have left behind detectable signatures that are still present in the CMB today. In the coming years, astronomers will likely use JWST and other advanced telescopes to search for these potential signatures, which could provide direct evidence of the multiverse and revolutionize our understanding of the cosmos. In conclusion, the discoveries made by the James Webb Space Telescope have forced scientists to reconsider many of the assumptions and theories that have guided cosmology for decades. From the detection of massive, well-formed galaxies in the early universe to the mystery of the Hubble tension, these findings challenge our understanding of the universe's evolution and raise the possibility of new, uncharted realms of physics. While some of these discoveries may seem strange or even fantastical, they are rooted in scientific inquiry and could one day lead to a profound shift in our understanding of the cosmos. Whether it's the possibility of universes merging or some entirely new force or particle, the future of cosmology promises to be just as exciting as the discoveries made by JWST. Who knows? We may be on the brink of an extraordinary revelation that could change our view of the universe forever.